Okay, so 11.3. The first of our convergence tests. This is called the integral test. And the idea behind it is we want to determine the convergence of a series by comparing it to an improper integral. So let me describe the setup. Let f be a function, but a very special function. It needs to be continuous, positive, decreasing function. On the interval c to infinity. Then if our sequence an, if we have a sequence which is equivalent to the function at the natural numbers n, or at x values which are natural numbers, then the series for an and the improper integral for f of x will have the same behavior. So let me write it up. Then summation of an from n equals 1 to infinity is convergent. I'm going to put this double arrow here. This means if and only if. So if this is convergent, then this other side will be convergent, and vice versa. So the other side is the integral from c to infinity of f of x dx is convergent. So that says convergent. All right, so it's also true, it's logically equivalent, that if this series is not convergent, so it's divergent, then it also has to be true that the integral is divergent. And if the integral is divergent, it has to be true that the series is divergent. So I could have written divergent here. And divergent here instead. But the upshot is, for us right now, we're trying to figure out how to determine if a series is convergent or divergent. We've already studied improper integrals, and so we can theoretically figure those out for more types of functions. So if I can switch from a series to an integral and answer the question, does this thing converge or diverge, it'll answer the question for the series also. Okay, so easy. Get into something here. Let's justify why this works, and then we'll do a few examples with it. All right. So why? So suppose we have, so remember the three conditions for our function. The function, it has to be continuous, positive, and decreasing. So our graph of the function is going to look something like this, probably. Sit down again. All right, so there's our function. This is f of x. And say this is c here. Or what do I want to call it actually? Let's this is the case when c equals 1. We can adjust it if we had to, but I just want to keep it simple for the picture. All right, so the integral. Let me draw that. I'll erase this, but the integral from 1 to infinity of f of x dx. What that looks like in our picture is it would be the area underneath the curve from 1 to infinity. So that might be a finite area or it might be an infinite area. If it's finite, that means this integral is convergent. If it's infinite area, this integral is divergent. All right, so what I want to do then is relate that to the series. So we're assuming that the sequence an is basically this function. It's just occurring only at these whole number inputs. So what I want to do is make a geometric interpretation of the series. All right, so one way I could do it is A1 would be, when n is 1, I go up to the curve, and that y value is my A1. Now, to give it a geometric interpretation, I need to make an area out of it. Tap it. So let's make a rectangle that meets the curve. With that, it has a width 1. So if I draw it like that, this rectangle here would have size, have area A1. Because its width is 1, its height is A1. And I do the same thing for A2. I have a rectangle with area A2. A3, A4, and so on. And so the series, which would be summation of the ANs from n equals 1 to infinity. Now there's a slight issue here, but basically the way I've drawn it, the series is the sum of these rectangular areas. And the way I've drawn it, you can see from the picture, the rectangles are all underneath the curve. And they will continue to be underneath the curve because I'm always drawing them so that they meet at the right endpoint. And since it's a decreasing function, the right endpoint is lower than the left end would be. So the rectangle, if I use the right endpoint, will be completely underneath the curve. So there is one issue. My integral doesn't start until 1, but that's just one extra term that I just kind of ignore. If I add up A2, A3, A4, and so on, what I get is this. The summation from n equals 2 to infinity, that's less than or equal to the improper integral. So therefore, if I already know that the integral is convergent, that means this series also has to be convergent. And if this series is convergent, if I add one extra rectangle to it, it's still a finite answer. So this picture, the way I've drawn it here, this picture tells me that if the integral is convergent, then the series is also convergent by this comparison. Okay, so on the other hand, let me draw the rectangles a different way. This time using left endpoints. So I want to have my points on the curve, but now I'm going to draw a rectangle that's poking out like this. Still has width 1, but its height is determined by the left endpoint. So this first rectangle would be A1, and it's poking out above the curve. And I do that for each of them. This would be A2, this would be A3, and so on. So it'd go on forever. But now this time, the curve is completely underneath the rectangles. It's completely inside the rectangles. So the area under the curve is contained in the area of the rectangles. That tells me that my series, summation of the ANs, is bigger than or equal to the integral of f of x. And so that tells me if the integral is divergent, and this is bigger than divergent, it also has to be divergent. It also has to be infinite. Bigger than infinite has to be infinite. So I can successfully compare my series to this integral in either direction. So we can get divergent or convergent depending on the answer for the integral. Cut this out, but now I'm thinking of something. Okay, so these pictures here and this argument is a little bit rough. I'm not trying to be rigorous about this. To formally prove this, we need to look at the partial sums. I don't want to get into that at this point. But this is the general idea. When I say these are true, this doesn't make sense if this is divergent. I mean, if this is divergent, it doesn't really make sense to compare the two because they don't actually have values. So when I write this and try to compare it, the fact that it's improper means I can't really make a comparison formally unless I know it's convergent, but the idea is there if we allow ourselves to have infinity involved. But I don't want to formally go through the partial sum form. Instead, I want to spend my time talking about examples. Let's look at the summation of 1 over n squared. And want to answer the question, is this convergent or divergent? So I want to use the integral test. So the first question is, can we use the integral test? So before I can integrate, I have to make sure that I have a situation where all the requirements of the integral test apply. So the first thing I do is I take my sequence, 1 over n squared, and I write it as a function f of x. So in this case, f of x would be 1 over x squared. I replace n by x, and first question is, does it make sense as a function? So for example, like we talked about a few videos ago, if there's an n factorial involved, x factorial doesn't make any sense, so we could not use the integral test in that situation. It has to turn into a function that actually makes sense. All right, so then we have to answer the question, where is this continuous? Well, 1 over x squared, that'll be continuous as long as we don't include division by 0, so as long as we don't have division by 0 on our interval. So if I limit myself to positive x values, we want a closed interval, so let's start with 1. It's definitely continuous on 1 to infinity. I don't care about the entire, all of the intervals of continuity. I just care in finding some interval that starts at a number and goes to infinity where it's continuous. So, yes, it is continuous on 1 to infinity. Next, we needed it to be a positive function. So I need to have a function whose outputs are all positive. Well, since it's x squared on the bottom, that'll always be positive. But just for emphasis, specifically on this interval we found, it is positive. So yes, it is positive. And then the third thing was decreasing. So we need to check continuous, positive, and decreasing. So for decreasing, once I have a function, generally the way you figure out is it decreasing or where is it decreasing, take its derivative, f prime. F prime of x would be, well, this is x to the minus 2, so that would be negative 2 x to the minus 3, or negative 2 over x cubed. Okay, so then the question is this derivative negative on the interval that we're looking at? And, well, we're looking at an interval where we only have positive x values, so this is definitely less than 0 because it's a negative number divided by a positive number. So yes, on 1 to infinity, this is decreasing. So what we have done, and what we have to do in general to use before we use the integral test, is we have to find an interval of this form where it's a number to infinity, where this function that we're looking at meets all three of these criteria: continuous, positive, and decreasing. All right, so the answer is yes, we can use the integral test. That means I want to integrate the interval we chose was 1 to infinity, so I need to integrate 1 over x squared from 1 to infinity. So our first step was verify that our function meets the three criteria. If it does, then the next step is an improper integral problem, the type that we dealt with back in section 7.8, I think. Chapter 7, section 8, I think. So we still have an integral to deal with. This was not a particularly hard integral, but let's review the way it works. Improper integrals, where the top is infinite, what you do is you replace that infinity with a new variable, say t. And then we take the limit as t approaches infinity. Then we have this limit, but now we need to integrate this. This is x to the minus 2. So when I integrate that, it becomes x to the minus 1 divided by negative 1. So that's 1 over the negative 1 over x. And we plug in our two values. So we have the limit as t approaches infinity of negative 1 over t minus negative 1 makes it a plus 1 over 1. And now as t approaches infinity, 1 over t approaches 0, so I'm left with just 1. So that 1, I circled it, that's maybe misleading. That 1 as our answer tells us that the integral 1 over x squared, it converges. And its value is 1. Now, be careful. Converges for integral tells me that the series converges. So my answer for my series is it converges. I don't know what its value is. It won't be the same value as 1. Okay, so the behavior is the same. If this converges, then this converges. But just because I know the answer to this doesn't mean I know the answer to this. Just because I know the value of this doesn't mean I know the value of this. So this 1 doesn't help me with this. At least not yet. Later on, we'll see that we can maybe use it to help estimate the value of the series, but it's not the exact value. All right. Similarly, we could look at a series like this, summation of 1 over n to the p. This is called a p series. And the question is, does it converge or diverge? Well, this is very similar to something we did back in chapter 7.8. We looked at these integrals that were of the form 1 over x to the p. From 1 to infinity, for example. And it turned out we were able to answer the question, for what values of p does this integral converge, and for what values of p does it diverge? And so I'll leave it as an exercise, but you can check that this function is continuous, positive, and decreasing on the interval 1 to infinity. So our integral test applies for this series, and since we know the answer for all of these, we therefore know the answer for all of these. And so what it was this converges, or convergent, if p was greater than 1, strictly greater than 1, and it was divergent if p was less than or equal to 1. So if that exponent was small, we had a divergent integral. If it was big, we had a convergent integral. So the answers for this type of improper integral are also the answers for our series, or p. So this is called the p series test, and it's a direct consequence of the integral test. Okay, so this is very important to know when you have a series like this, where it's 1 over n to the p, 1 over n to a power. That power immediately tells you, is it convergent or divergent? All right, let's do maybe another one. All right, so n times e to the negative n squared from n equals 1 to infinity. All right, so thinking ahead, if we didn't know what chapter this came from, and the question was, is this series convergent or divergent? A hint would be, if I think of this as a function, the function would be f of x equals x times e to the negative x squared. And that's a type of function that it looks like I wouldn't have too much trouble integrating, because it's a substitution situation. We have an exponent, x squared, we have basically this derivative in front of it. That's a u substitution situation. So we wouldn't have too much trouble integrating that. But before we can use the integral test, I have to verify that it applies. So we need continuous positive and decreasing. Okay, so let me approach this slightly different so I can make a point. Generally, no, that's too strong. So generally, it's easiest to check it in this order. I mean, continuity is the simplest thing to check. Then positive is a little bit harder sometimes. Decreasing is harder because you have to take the derivative. So continuity, where is this continuous? Well, it's continuous everywhere. I never have an issue with this function. I never have an issue with dividing by 0 or anything like that. So this is continuous everywhere, from negative infinity to positive infinity. Well, it's positive. Where is it positive? Well, e to a power is always positive. X, however, can be positive or negative. So the sign, positive or negative, of this function will be determined by x. So as long as x is positive, the function's positive. So it would be positive from 0 to infinity. But I don't want open intervals generally for the integral test. I want to have a definitive starting number. So if it was 0 to infinity, I'll make that 1 to infinity starting at 1. Right? Now these are different answers, but that's okay. Of these two, which one do I pick for my interval? We'll pick the smaller interval, so the bigger starting point. I don't need to start at negative infinity. I can start at 1. So I can go back and change this on continuity to start at 1 and be 1 to infinity. Right? So as you answer the next one, we'll do it explicitly, but if the next one I was able to say, well, I know it's decreasing from 2 to infinity, then I could go back and say, well, if it's positive from 1 to infinity, it's also positive from 2 to infinity. I just, at the end, need to have a single interval that gives me makes it work for all three of these criteria. Okay, so let's figure out decreasing. So for decreasing, I need the derivative, f prime. This is going to be a product. So derivative of x is 1, e to the x squared, plus x. Derivative of e to the negative x squared would be negative 2x e to the negative x squared. So that gives us 1 minus 2x squared e to the negative x squared. All right, so now the question is, if this is f prime, is this negative? I want decreasing, so f prime needs to be negative. Well, e to the minus x squared is always positive, so I just need to make sure this is negative. So I need 1 minus 2x squared to be less than 0. So that means 1 needs to be less than 2x squared. So 1/2 needs to be less than x squared. So if x is at least 1, this requirement will be satisfied. If x is bigger than or equal to 1, when I square it, it's even bigger. So 1 to infinity works for decreasing as well. Right? So I don't have to adjust my intervals anymore. So, therefore, I can use this function, I can use the integral test with this function on this interval to determine my answer for the series. So I'm integrating from 1 to infinity again. But again, that 1, it has nothing to do with this one. I just need to find a value that works. A x value that from that point onward, those 3 conditions are met. It doesn't have to be the same number from the sum. So I want to integrate from 1 to infinity x e to the negative x squared. Like we said, this is need more space. I'm going to integrate from 1 to infinity x e to the negative x squared dx. So we turn this into a limit as t approaches infinity. And then, like I said, this is a u substitution. U equals negative x squared. Du would be minus 2x dx. So my integral would be, I don't have the negative 2, so this is du divided by minus 2. So negative 1/2 du, and then e to the u. Now, because it's a substitution, because I made a substitution, I can't write the same x bounds. I can't use the same bounds because those were x bounds. I need to use u bounds, so I plug these values in place of x. When x is t, u would be negative t squared. When x is 1, u would be negative 1. All right, so then the integral of this would be negative 1/2 e to the u. So I'll get negative 1/2 e to the minus t squared. Minus a minus makes plus 1/2 e to the minus 1. Okay, so now, after all that, we have a limit to evaluate. As t approaches infinity, the only place t appears is right here in the exponent, and it's negative t squared. So that's going to be e to the negative infinity. In formula, that's e to the negative infinity. Infinity squared is infinity, with a minus sign is negative infinity. E to the minus infinity, that's 1 over e to the infinity, which is 0. 1 divided by infinity is 0. So this first part's 0. My answer then is 1/2 e to the negative 1. And all I care about is that's an answer. That's a finite answer. So our integral's convergent. So our series is convergent. All right. So the point of the integral test is we can evaluate series, convergence or divergence by evaluating an improper integral in the proper situations. So the big thing is, when you're trying to use this, you first have to verify that your function satisfies the 3 properties: continuous, positive, and decreasing on some infinite interval. And then you have to actually integrate. The integral test will tell us, if it's successful, it'll tell us the series converges or the series diverges. It'll say that definitively if we're able to apply it. However, it does not tell us the value of the convergent series. We can use it to estimate the sum of a series. So if the integral test applies, I don't want to spend too much time on this. If the integral test applies, that means we have a function of the right type, and the series is convergent, then we can say the following statement. Let me be a little bit more careful. So if we can make it apply eventually on some interval, say k to infinity, and we have a convergent series, then we can say that this series, its value is between two things. Okay, so rather to avoid having too much, well, either way, I have to have notation. It's less than or equal to the partial sum sk plus the improper integral from k to infinity so let me just reiterate. Sk, that's the partial sum where I'm adding up these terms from n equals 1 to n equals k. So rather than going on forever, I stop at k. So that's a finite sum there. I can definitely compute that. It's just adding up k numbers. The improper integral k to infinity, that exists. If this is convergent by the integral test, this is also convergent. So that tells me that this is just an integral problem. If I'm able to integrate it, then I have an answer for it. I get a number for it. So this gives me a definite number that this infinite series is less than or equal to. On the other hand, we can find a similar thing that is definitely bigger than. So it'd be sk plus the improper integral, more space probably, sk plus the improper integral from k plus 1 to infinity. Right? So this is very similar. If the integral test applies starting at k, it also applies starting at k plus 1. So if it's a convergent series, this integral also is convergent. So we can compute its exact answer and add to it the exact answer for the kth partial sum. So this will be a number. And it'll be smaller than this integral. This is definitely smaller than this because you're integrating less of the area. So our series, its exact value will be trapped between these two numbers. And basically, the bigger k gets, I'll just say this without justifying it really, the bigger k I use, the less of a difference there'll be between these two ends. So this number will get closer and closer to this number if I use larger k's. So I can ask the question, how exact or how precise do I want to estimate the series? And once I figure that out, once I answer that question, I can figure out, well, how big of a k should I use to trap the exact value between these two numbers? And then I can compute these two and say the answer for this series is within whatever decimal place, whatever error I want of this number here and this number here. Okay, so we can estimate this to whatever accuracy we want by picking a large enough k and then computing a partial sum and an improper integral. Okay, so I don't want to prove this. I don't want to say anything more about this other than just give you a very brief explanation for why this is true. Basically, let me say it like this. If you look at one of these two expressions, sk plus this integral, like we said, sk is the kth partial sum for this series. So I'm adding up the first k terms in this sum. So like a1 plus a2 all the way up to plus ak. But if I want the exact series, the exact value of the series, I still have the rest of the sums to go. So that would be n equals k plus 1 to infinity ak. So I have this remaining sum that's not in the partial sum. It's the rest of the series that's not covered by the partial sum. We can call that like a remainder series. So that remainder series is itself an infinite series. And just like when I was justifying the integral test, we can trap that series underneath the curve in two different ways. And so we can get that it's bigger than this integral, and we can get that it's smaller than this integral. So my series, which is this plus this, is trapped between this and this. Okay. There's an explanation in the book as well if you want more information. I just wanted to briefly touch on this. For our purposes, for problems, the questions would be, here's a series, here's a specific series, use the integral test to determine whether or not this series is convergent or divergent. And to do that, you want to first show that it is applicable by checking the three conditions. This extra stuff about approximations will not be something I would test you over. Right, so that finishes up completely 11.3. So we'll stop the video there. And then continue with 11.4 next time.